Right, we'll get started then. So I'm Kev Sheldrake. This follows on from the talk yesterday where I talked about HiTag2. Yesterday I talked about the first attack in the paper Gone in 360 Seconds by Garcia and Balash, and today I'm going to talk about attacks 2 and 3, which are even cooler and more interesting attacks. But I will recap on what we did yesterday because I realise we've all been drinking and sleeping since then, so it probably kind of makes sense. But I will go through that faster than I did yesterday, so I'm sure it'll be good. So there's the who am I slide. Obviously I work in cyber. As I say, we're going to cover attacks 2 and 3. So this is a workshop format as opposed to the talk format that we had yesterday, so do feel free to ask questions. There's no like exercises, there's nothing for you to necessarily need to do apart from like watch and understand, or you know, but feel free to interact and ask questions as we go, so that it makes some sort of sense. I'd rather you understood it than kind of just thought that was 2 hours I'm never going to get back, as it were. There's quite a lot of maths. Don't be scared of it, obviously. It's not quite the same, it's very crypto maths, so there weren't really numbers, it'll all be symbols and XORs. Right, equipment. So yesterday I didn't really talk about equipment, but I thought I'd chuck it into the workshop because we've got a bit more time. I don't really need the full 2 hours to crack on through these attacks, so I'm just going to fill it out a little bit. In order to do this work, I needed a HiTag2 reader and some tags, and like I said yesterday, the reader I was using was non-standard, so it did other stuff. The protocol was different to the standard HiTag2 reader, but if you're going to do something along these lines, you're probably going to want a reader of some sort. Say Adam Laurie sold me a Frosh and I got through 3 of them and I've still not managed to get one that works, which is really annoying. But the Frosh design is like the standard HiTag2 reader design, so there'll be an HTRC 110 chip which does the analog front end. There's like a massive sort of PDF on designing the front end that fits on that, but it's a few passive components and an antenna, and that has a serial-ish kind of interface which is controlled by a PIC. I think it's like a 16F on the Frosh, but that's all there is. And any other HiTag2 reader you come across pretty much will be that design to some degree. I did see, and I bought a Raspberry Pi Shield, which is based on the same design, but it claims to only do password mode and not crypto mode. And I imagine that's because they've got an old version of the firmware on the PIC or something. I'm not really sure, or they didn't quite work out entirely how to make crypto mode work. But they're around. I'm going to bodge that into being one that can do crypto mode, just because I want one that works. But yeah, as I say, they're hard to find. So if you do work for like an access control company, like building access control, things like that, then yeah, use all your channels, and if you can find one, I'll quite happily buy a HiTag2 reader off you. Okay, so for eavesdropping on what I was doing, I used the Netis USRP1, which I don't know if you all know, but it's like a software-defined radio. Sort of losing people because I'm talking about equipment, so there it is. It was really useful just to see what was going on. So as I was writing code and making it do stuff and interacting with the tags or interacting with the reader, it was nice to be able to actually see the waveforms and know that what you'd got was what you were expecting, like manually decode stuff from the frequencies and that. RB's a tool I wrote. I'll show you a screenshot in a second, but it's not released yet. Proxmark 3, because of course you need a Proxmark. Our Fiddler, so the MP Lab IDE is yeah, with the full kind of suite for like taking the code from GitHub and actually just modifying it and recompiling it yourself. Apparently before me, no one had actually offered any updates to the GitHub for our Fiddler, but the idea is that you all do, because there's lots more you can do with it if you want to hack the code. And then like for back-end stuff, logic analyzers, Arduinos to mimic the back-end, lots of code, lots of stuff. So that's a tool, that's RB. The idea, so in GNU Radio, it's really good for instantaneous stuff, but when you're like pulling out data, or you're pulling out data traces that you can't quite decode because your software is not quite right, then you want to be able to see what actually happened in time at what point. So basically I tap my flow graph at lots of different points at whatever frequency it's moving at that point, and store them all to files, and then Arby loads all those files in and lines them all up over the top of each other, so you can sort of see what's going on. And you can also line up like multiple kind of sessions, so you can see like here's a good session with a real card, and here's a bad session with my emulator that doesn't work, whatever it happens to be. But one day I'll release Arby. It's quite there's all sorts of radio-y stuff you can do with that. Right, so the academic paper. Now this is where we speed up, and I'll quickly rack through what we did yesterday. So there's an academic paper called Gone in 360 Seconds by Vidal, Garcia and Balash. If you haven't read it, I recommend you read it. It's free on the internet. It's very easy to find. It's about 16 pages, and the maths will make your eyes bleed, which is why I'm kind of doing this talk. HiTag2, 8 pages, 32 bits each. Page 0, the UID is public. It's not used for access control decisions typically, but it is the first page. It's provided as part of the crypto handshake and is used to see the RNG. Pages 1, 2 and 3 contain the crypto keys and the tag password, there for the mutual authentication and to see the PRNG, which sets up a stream cipher. And pages 4 to 7 holds the user data, which identifies the person who's the card's for, and that's what the access control decisions are made on. It's pre-shared keys and mutual auth all round, so every reader in a system's got the same key, every tag in the same system's got the same key. That means that if you attack one reader and get the key, you've got the key for the entire system, and equally the same goes for the tags. So you could be an insider with your valid tag that only gets you into the ground floor, hack that, and then copy people's tags that get you into the top floor. You could be a contractor and hack your contractor's pass. You could find one in the street, you could copy one in the pub. There's all sorts of attack methods that red teamers might want to use to get in. But if you're only attacking the reader, attack 3 will let you attack just the reader without actually having to have a tag, which is even better. Which is what we're going to come to. So crypto mode looks a bit like this. As you can see, every step is encrypted after the first one. They exchange the nonce, which seeds the RNG, and the challenge response value, which is the encryption of OXFFFFFFFF. That means that the tag can guarantee that the reader knows the key that the tag's got. When the tag responds with its password encrypted, then the reader can confirm that the tag knows the password as well. And then they've mutually authenticated. And from there onwards, they can have an encrypted communication where the reader can send commands and the tag can respond. So the overall, what's missing from this is UID. So the tag's UID is passed over, and the reader seeds its nonce, seeds its PRNG with the nonce, the key, and the tag's UID. The tag does the same. The nonce gets sent encrypted across. It all gets fed in. We'll talk about that. It turns into a stream cipher. Stream cipher is XOR. Yeah, we all can remember where we were yesterday. Yeah. So here's the PRNG being seeded. It starts with the UID in the lower 16 bits of the key. The reader invents a nonce. It XORs that with the upper 32 bits of the key and shifts it in 1 bit at a time. And as it does it, it gets PRNG output. And as it gets the output, it XORs that with the nonce it's created to encrypt the nonce, which can then be transmitted to the tag. The tag starts in the same situation. It receives the encrypted nonce. It XORs the output of the PRNG 1 bit at a time with the upper 32 bits of the key and the encrypted nonce that it's received. And for every bit that it XORs, it retrieves 1 bit of NR XOR key, which it can then push in, and that will put it into the next state where it can get the next bit out of the PRNG. It's a really neat way of like seeding and decrypting at the same time, which I really like. If you try and do the whole 32-bit word at once, you can't, because you don't have the PRNG output to do so. But you do it 1 bit at a time, you can, which I quite like. I mean, it doesn't make it secure, I just quite like it. So the reader, after it's sent the encrypted nonce, ends up in this situation, and so does the tag, which means the PRNGs are in step. They're both going to produce the same sort of pseudo-random output, which is what's going to be used for the stream cipher. So one end will take the same number of bits out of the PRNG that it's got for its data to encrypt, XOR the two together, that'll give encrypted data, send it to the other end, that'll get the same number of bits out of the PRNG, which will be the same key stream, XOR that with the encrypted data, and that will return it back to the original data. After it's been seeded, both of them enable the feedback function, so there's no more seeding data. It's just you run a function on the state, and that produces the new bit that's going to get shifted in every time you kind of shift the PRNG to take a bit of output. This is the encryption and decryption steps, as we talked about. The feedback function is basically the XOR of 16 bits of the PRNG. If you don't know the state of the PRNG, then you can't predict what the feedback function would return as a 0 or 1, so you can't predict future states. It's quite sound. LFSRs have been around for ages, and they are used in lots of places. I'm sure they're normally secure, just not in this case. The output of the PRNG, that's not the bit that just gets knocked off the end. It's produced by a filter function F, which is made up of a hierarchy of filter functions A, B, and C. Each of the A's and B's takes 4 bits each, so that's 20 bits coming from the LFSR PRNG state. Each of those produces 1 bit of output, which gets fed into function C, which produces 1 bit of output, and that becomes the actual output bit. All of these are 50-50 biased, so if you don't know the bits going in, you can't predict the output at all, which looks quite random. This is how they're made up. I don't think I included these slides yesterday because we didn't need to know about the filter function yesterday. We will today, but we didn't yesterday. So you can see they all take 4 bits and they produce 1 bit of output. They're implemented using Boolean tables, which is quite a common thing in hardware because it's really easy to implement. So if you've got 4 bits going into function A, you turn that into a 4-bit number. So it's got a value between 0 and 15. It's basically going to look that up in a 16-bit number and pick that bit position, and that bit position will either be a 0 or a 1. Same for function B. So you can see like OX2C79 has got an equal number of 1s and 0s, 6671 again an equal number of 1s and 0s. So if you don't know the input bits, you don't know where in that Boolean table you're going to be picking the bit, you can't predict if that's going to be a 0 or a 1 because you've got a 50-50 chance. Equally, they all produce 1 bit each. That gets fed into function C, which is obviously a 5-bit number, so values 0 to 31, which looks up in a 32-bit Boolean table. So there's 32 1s and 0s there, of which 16 are 1s and 16 are 0s in some sort of kind of random function. For HiTag2, these numbers are fixed. So if you've got your own HiTag2 system, there'll be these numbers. But as I say, they're 50-50, so it's really hard to predict if you don't know internal state information. So far, so good. So there's the picture of the function as it's very biased. So it looks like it looks pretty good, I would say. So as you go through the process, we get to the commands at the bottom, HiTag2 commands. So I talked about this yesterday. I'm going to go through this quickly. There's 4 commands, 2 of them are read commands. CM0 is a 1 if it's a read command. A2, 3 and 4 makes up the page number that we're going to read or write or whatever. Now a command is actually a minimum of 10 bits. It has to be the normal 5 bits followed by the 5 bits inverted, like sort of XORed with FF essentially. Because that provides integrity. When it gets decrypted at the tag can check the second block is the inverse of the first block and therefore know that nothing's gone wrong or screwy in the comms. You don't want to have a write tag command received when you're actually meant to send a read tag command. You might mess stuff up. But you're not limited to 2 blocks. You can have as many blocks as you want, as long as they follow the same format of normal, bit inverted, normal, bit inverted, normal, bit inverted, etc. And you can literally have thousands of these in a command, and the tag will quite happily check these as they're received, and then act, assuming that the integrity holds up, act upon what the command said to do, which is hilarious. And it's what we abuse in the attack. So in the paper there's 3 attacks. The nonce replay and length extension attack we looked at yesterday, which is for key stream recovery, but there were 2 more attacks. So basically, if the keys are read protected, then you can't read them out even if you know the key or the key stream. So attacks 2 and 3 then kick in because they can be useful for getting the key. So quickly, nonce replay. I can skip through this, but there's at least one person in the room who didn't see this, so I sort of feel like we should probably cover this quickly. And also, we're going to need this for attack 2, so hey, let's do it. What you'll have noticed is that all the entropy in the system, given a single tag that the reader's talking to, all the entropy came from the nonce that the reader sort of came up with. The tag produced no entropy whatsoever. So if you can capture the encrypted nonce and the encrypted challenge response value as it's passed from the reader to the tag, and then you can emulate a reader, you can replay those values to the tag every time you initialize the tag, and that'll initialize the tag to the same state every time, which means the PRNG will be in the same state, which means the key stream will start from the same position and always be the same. And if you've got repeating key stream and it's all XORed, then from a crypto point of view, you can now attack that, because you can get multiple cases and you can XOR stuff together and pull out the key stream. So that's the nonce replay attack. We're basically going to always send it, we're going to capture one encrypted nonce and challenge response value, and then we're going to use that every time to make sure the key stream is always the same. So in pictures, that's after it's sent the nonce, you can see it's simply the key and the nonce. There's nothing else going on there. So that's what we're going to do. So as an example, if we had this encrypted nonce like 4A85B2DF, then perhaps the tag would respond with this particular key stream, and every time we initialize that tag, we'll get that key stream. So that's the kind of key bit about why we're doing nonce replay. So we're going to try and find the read page 0 command, because we already know the contents of page 0. It's the UID, which is broadcast at the beginning of the handshake in clear. So we already know the answer. There's the commands are encrypted, so they're 10 bits long. There's 1,024 possibilities, of which there's 16 valid ones. So we could root the entire space like this. But actually, we can do a clever bit flipping, clever attack where we only need to look for 6 bits. If we know that bit F of the encrypted command is going to decrypt to 1, and bit K is going to decrypt to 0, because the second half is the bit inverted version of the first half, and J, L, M, and N will decrypt to the inverse of what E, G, H, and I decrypt to, then we can actually hold J, L, M, and N as zeros, for example, or any values that we particularly like, and then we can brute E, G, H, and I until we find something that matches when they're both decrypted. Well, obviously we need to brute F and K, because we don't know what key stream they are, we just know what they decrypt to. So we only actually need to brute 6 bits, E, F, G, H, I, K, which is 64 states. So on average we'll hit 1 after 32 guesses. Does that make sense? Yeah, everyone's happy with that. Good. So once we found one valid read command, and so what we're doing, we're going to initialize the tag, send our guess, and just keep on doing it until we get anything without the unencrypted response, error response. And once we get something back, then we know we found 1. And then once we've got that, we're going to bit flip that to find all the other 15. So we know that F decrypts to 1 and K decrypts to 0. We know, E, G, H, and I decrypt to the inverse of what J, L, M, and N decrypt to. So we can flip bits. So because it's like an XOR, because it's like a stream cipher, we can XOR bits in the ciphertext, and that will we can flip bits in the ciphertext, and that will flip the corresponding bit in the plain text, which is really neat because obviously there's no real integrity protection. So, I mean, the integrity protection that they provide is literally for comms integrity, not for like cipher integrity, which is where they went wrong, clearly. So we can flip a bit and turn a read inverted into a read, or a read into a read inverted. We can flip a page bit and turn from one page read into a different page read. So if we flip all of those bits in a sequence, we can find all the other 15 possible commands. We've now got a set of 16 encrypted commands, which are all valid reads, and one of those is read page 0, which is what we're going to look for. So all we're going to do is initialize the tag, send 1, and test it, and when it succeeds, retrieve the key stream that it provides, and then we're going to use that key stream later to actually attack the tag. So the way we test it is we assume we're right. We assume it's read page 0, what our encrypted command decrypts to, which means that we assume the response we get back is going to decrypt to the UID, which is the contents of page 0, which we know because it's public. We XOR our guess with the read page 0, we XOR the response with the UID, and that will give us the first 42 bits of key stream, if we're right. We don't know if we're right, so what we do is we take the key stream and we make a 40-bit version of the read page 0 command, which is using that length extension, comms integrity that I talked about, and that's simply a case of build that read page 0 command, XOR it with the first 40 bits of the key stream, which will essentially encrypt it, initialize the tag back so it's starting with the same key stream, and send the 40-bit command. Now, you'll get back a 32-bit response. If it's the error response, then that means our key stream's invalid and our command didn't decrypt properly. So that guess is wrong, move on to the next guess and go and cycle through all 16. But when you get a response that isn't the error response, that means the tag successfully accepted that 40-bit command, which means it decrypted properly, the comms integrity stood up, it understood it, and therefore replied with what is page 0. At which point we can then XOR that with what we know is page 0, the UID, and we've now got another 32 bits of key stream. So we've now got 72 bits of key stream from this starting position of that replayed encrypted nonce, which is what I basically say here. So you can then use that key stream to read out every page of the tag, and that will give you these pages, hopefully, including the keys. I talked very briefly about, go get the code for our fiddler. The code I've written is all in the GitHub. I haven't actually checked. I should have checked. It should be live. It should be there. It's just C. Can you see some of that? This is my code. It's like really bad function names. And that's the comms bit, actually sending and receiving data. But you can pinch all of that from other bits of our fiddler because you can see it being done elsewhere in our fiddler. So these are the 6 commands I added, and I modified sniff PWM. So if you were going to do attack 1, you simply need to get one encrypted challenge response, nonce challenge response value, and then you run the HiTag crack, HiTag2 crack using those values against that card, and then it will crack the card. So, do you want to see that demo again? Yeah? Yeah, why not? It's not very interactive today. I'm like, so I have a HiTag2 card here. Right, we better find my our fiddler. Yeah, so there's our fiddler. In fact, I'll tell you what, because it wasn't so great, was it, yesterday in that width? There we go. So there's my new commands that I've added, and there's the sniff PWM modification that I added. I won't sniff the whole thing. I'll just use some values that I've got. So I've got files with like captured encrypted nonces and challenge response values because, like, he wouldn't saves me having to do it live. Where's my mouse gone? There we go. So hopefully you can see that. That's going to then, so it's searching for any valid read command, and then it's going to enumerate, sort of do the bit flipping and find the read page 0, and then it just pops out and reads all 8 pages. So that's the UID there. That is the lower 32 bits of the key, that's the upper 16 bits of the key, that's the config byte and the tag password followed by 4 pages of user data. So that's the normal attack. But if these pages are read protected and you don't get the key, you're then a little bit stuck. Once you've got the key, you can run HiTag2 reader, so paste that in, and that will just read whatever HiTag2 tag I've got that uses the same key. So you can see, yeah. So once you've stolen the key, you don't need to crack cards from that system. You can just go and obviously use the key to just read other people's tags, unless of course they have their pages read protected. So right, so I hope that wasn't too boring, kind of going back over all that again. I say copying tags is dead easy. Just stick it all into the V tag and then hit clone. When you clone, you need to know the tag password or key for the blank, which is in the datasheet for the blank HiTag2 tags. So as I say, the pages can be read protected, which means we do need different attacks. So attack 2, the time memory trade-off. Basically, the key's 48 bits long, so the key space is massive. It's too big to build a table for the entire key space, and the protocol is only about 5 kilobits a second, so it's way too slow to do an online attack. So we need to do some kind of offline attack. So the approach they took, the academics, was build a table for part of the problem and then do some kind of an online attack to get something to look up in the table. So what they do is they build a table of 2 to the 37 entries, which is big but doable. It's a 2048th of the entire space. So what that table consists of is literally PRNG states and 48 bits of key stream generated from each of those states. So what you then do is recover 2048 bits of key stream from the tag, and then you slide through that key stream looking for matches in your table. And the probability says you will have at least one match that will be a valid match. With high probability is normally what they would say at that point. In every test I've done, it's always found it. So, so in my small sample set of 50 tests out of 2 to 37, it worked. So from there you can roll back the PRNG state to the initialization steps where you can extract the nonce, and then you can XOR that with the key bits to get the key out. Okay, so to build the table, you need to start from a random state. All zeros is not good because it doesn't really shift in correctly. So you just pick some random state, store the 48-bit state, generate 48 bits of key stream, store it with that, and then just advance from the stored state by 2048 states. And then, and this is the big then, sort your table on the key stream output. Now you can't pre-sort it as you go unless you build some massive kind of binary tree, which I found impossible. So I'll come back to it, but I've had multiple attempts at building these tables efficiently, and I can't find a really good one. My first attempt was going to take 9 days. I got it down to 2 days by the end of it. Yeah. So this is interesting though. So in the paper, they when an academic writes the next proposition introduces a small trick, yeah, what they mean is magic, right? Because now I've searched for this and I can't find anywhere where this is in somebody else's paper. So this must just be something that is generally known about linear feedback shift registers that I don't know, or I didn't know. They also use the word intuitively, which is again is another synonym for magic. It means that I'm not going to tell you how this works, but you just have to trust me. Now I stared at this equation on and off for about 3 weeks before I finally understood what it was actually saying. And what it's actually saying is really straightforward, and you'll go through the next few slides and kind of think, well, why was that so hard? But yeah, it didn't make sense. I'll explain when I get there. What it's saying is that the difference between the linear difference between a state and the nth successor. So say the So for n, we're going to assume 2048 for this, for all of this, but I use n all the way through because it's a generalization, right? But between a state and the state you get to 2048 cipherticks later is the linear differences between those two states is a combination of the linear differences between each of the bits in the starting state having been advanced 2048 states. So essentially what we're going to do is if we created 48 states where each one only had one bit that was a 1, right? So we start with like all zeros and a 1 on the end, and then like shift it in, shift it in, shift it in, all the way through. And we jumped those forward by 2048 states. We'd have like destination states for every bit. We could then look at any random state that we wanted to advance, and for every bit that's on, take the corresponding destination states that each of those individual bits gets to, and XOR all of those together, and through the process, literally magic, that will give us the state you'd have got to had you moved state S forward 2048 states.
So it's kind of like a lookup table for just an individual bit.
Yes. But why can you XOR them all together? That's what I don't understand. I still don't get why it works, but I've tested it. It definitely fucking works. So, so I'll give it, right. So put that into context. So D0 would be the state, the nth successor of the state where bit 0 is a 1. D1 would be where bit 1 is a 1. D2 would be where bit 2 is a 1. And you build up 48 of those. And then if like S was this 48-bit state, which I've shortened for brevity, then for each one you take the destination state and you just XOR the whole lot together. So bit 47 is not on, so we ignore that, but bit 46 and 45 are, so we take D46 and D45, and we also take D3, D2 and D1, but obviously not D0. XOR all of those together, and that'll advance S by 2048 states. The reason why one of the reasons why this equation was so hard to understand is because DI is a 48-bit state, but SI is a single bit. I don't know, maybe I'm just not used to the way academics write stuff, but I would have expected them to have been of the same sort of size, and so I was being very confused by that. But yeah, that's kind of what we're doing. So that's what the equation means, which is really simple when you look at it like in those terms now, I think. But I just did not understand what that was saying, or why it would work. That's the other thing, I suppose. So pseudocode for building the table, it's really straightforward. You just keep on moving the bit through the state mask. The LFSRN step is just a function to step it as many steps as you want it to step. And then to actually do the jumping, again, really straightforward. You're just checking which bits are on in the state and then XORing in the D states, and that will do the jumping. Now the reason we're doing this is because if n's 2048, which is the value we need for this, then building the table takes 100,000 cipherticks, which is done in a split second. Like, you don't even notice it. But when we come to jump through the table, we do that 137 billion times, and those fractions of a second really add up. Whereas instead of doing 100,000, instead of doing 2048 cipherticks for each one of those, we can do up to 48 XORs, which is clearly a lot faster. So it is really worth doing, and it's something I'll be using in the future whenever I see an LFSR. The way I built the table was I multi-threaded it across all the cores, all the virtual cores that I had available. So, and instead of if you imagine the space that you're going to kind of step through, instead of trying to do one core has this bit and one core has this bit and one core has this bit, I interleaved them all instead. So I just kicked every core off 2048 steps apart, and then each one jumps forward. If I've got 8 cores, it would mean 16,000 whatever steps, so they all kind of overlap each other. It just meant I didn't have to have lots of crazy, you can imagine jumping to the bottom block to start the bottom block. It's how many cipherticks is that going to be? It's ridiculous. So instead of, or how many I mean, sort of, you've got to do that XORing like 8 times or something to get there. But so, yeah, it was just an idea. But it worked. So I have 2 D tables. I have the 2048 table for getting the starting points, and then I have the 2048 times how many threads I've got to be the actual jump table for jumping through the blocks. Because it doesn't matter what order you build them in, because they're random anyway. It's literally a pseudo random number generator, so there's no benefit to building it in any particular order because you can't predict what you're going to get. Right, and then you need to sort it, right? And you can't. Well, I didn't find any way, and I did talk to some good computer scientists, but I couldn't find any good way of sorting it as I was generating it. So instead, I decided to generate it and then sort it and then sort the subtables afterwards. I found that seemed to be faster. I was doing it all on a USB 3 disk, and the bottleneck on USB 3 is ridiculous. Like, you know, everyone tells you USB 3 is quick, but it's not. It's like it's just as bad as anything else. So yeah, you want to do it on connected side disk, but because I'm like a Mac household, you know, I've got like machines you can't take apart or machines that have already got all their bays filled up. And the only Linux boxes I've got are really old and manky. So yeah, you want a better computer than what I had, basically. So this is what we're going to do, right? We've built the table. We're going to get 2048 bits. We're going to slide through it in windows of 48 bits. We're going to find matches. We're going to test the matches to make sure they're valid, and then we're going to roll it all the way back. So I'll quickly go through. So we'll use attack 1, but instead of getting 72 bits of keystream, we're going to just keep on repeating that attack. So if you've got 72 bits of keystream, you can make a 70-bit read page 0 command, and then that will get you another 32 on the end of that, so you get to 102 bits. And if you've got 102 bits, you can do the same thing, make a 100-bit command, and then keep on advancing along those lines. The R Fiddler, the wonderful piece of equipment that it is, limits the commands to 512 bits. So if you want 2048 bits, you're kind of slightly stuck. So I wrote it to consume the key stream and then kind of send a command. So you just don't. So you don't reset the session, but you basically to keep on sending commands, which are the read page 0 commands you already know the answers to, just to use up the key stream, and then you eventually get to the point where you've run out of key stream, and then you send your. Well, you need to keep 10 bits back so you can send a command, and then you can get your response. So it's just a bit more complicated than like when the guys did it on Proxmark. Not that I've seen their code, but as I understand it, they could just make their command as long as they wanted to make their command, and it just worked. It's just on our Fiddler, you've got to be. I had to write a silly little loop that did a bit more work, but hey ho. Sliding window attack, really straightforward. Each of these slices will be offset by 1 bit, so we're just going to slide through 1 bit at a time. When we find a match, that will recover the PRNG state, and then we'll do one or other of these depending where we are in the stream. So typically I roll that state forward by 48 bits and recover the next 48 bits of keystream and compare that in the recovered keystream to see if it matches. The only time you can't do that is if you're within 48 bits of the end, so instead of going forwards you go backwards 48 bits. But you need to do this because you will get random matches. It was like it was blowing my mind when I was writing I wrote a test handle for it, and I'd go like generate me 10 test cases, and the first test case would always succeed and find the right key, and the second test case and all the others would all fail. And I was like, something's wrong with my code. So, and I got the point of like generating individual test cases one after another, like with separate runs of the program to make sure there's no like variables interacting. And I still would have the first one would work and the second one wouldn't, and I was just like, why? And it was just complete random luck. But all it was on the first case, the match I had was the right match, and on the second case, the match I had was just a pseudo match and wasn't the right state because I wasn't doing this test. But so, at least by writing the test cases, it forced me to realise that I had to be a bit smarter and build that in. Rolling backwards, right? if you know the state of the LFSR, it's dead easy to roll backwards. It's basically function L shifted by a bit, and that will generate the new bits that got lost before. So we can go backwards. Once we've found the PRNG state and we've confirmed it's the right one, then we know what offset we are in that 2048 bits of key stream. So we can roll back all the way through to the start of that key stream, and then we can roll back through the handshake. So it would be page 3 would have been received, and then the challenge response would have been sent, and then you're at this point where the encrypted nonce has been sent. Well, we want to decrypt the encrypted nonce. We have the encrypted nonce, but we need to decrypt that because we want to get the key out, and the key is XORed with the nonce. So when you get back to that point, you then roll back by pushing in the UID and recover 32 bits of key stream as you do it, and then you can XOR that. And well, in fact, there's the maths. You can just XOR your encrypted nonce that you've captured with the output that you've just recovered. That'll give you back the original nonce. Go back to that state that you had it in, where the nonce XORed the key is in there. XOR that, out pops the key. Now you have the key. Okay. So the table is 1.5 terabytes, so it fits on a 3 terabyte disk. Yeah, it was fun to do. I spent this attack took less time to understand, but I spent the most amount of time on it, trying to improve that like building and sorting algorithm, because it just felt wrong, and I just couldn't. But everyone you speak to kind of goes, "Oh yeah, why don't you?" And then whatever they say, you kind of like either, "Yeah, I've tried that, and here's why it doesn't work," or "That won't work." And then they kind of scratch their heads, and then they kind of like feel really embarrassed because they think they know a bit about programming, and then they wander away. And they come back a few weeks later, going, "Yeah, I've got absolutely nothing. I've got no." Someone's like, "Use a database." I'm like, "Yeah, okay, then. Yeah, let's use a database. I'll go on Wikipedia and find out what the insert times are." Ridiculous! Like, you want to insert 2 to the 37 items in a database? Good luck. Like, you'll be here for weeks just inserting the data. Yes, it will be sorted when it gets there, but you literally can't get the throughput on the I/O to actually insert into a table. So, and if you try and import, it's just as bad because they do inserts behind the scenes. So of the commands, there's a keystream command that I wrote, which does this, and then so the way we do it is build the table once, get the UID, get some encrypted nonce encrypted challenge response value, and use that to get keystream. Copy the keystream into a file, and then just run the search against that. So let's do that. So no keystream, no keystream. You can see no keystream, right? But we've got an encrypted nonce there and challenge response value, and that's for that tag. If at any point this doesn't make sense, just shout. Yeah, it is interactive. So it's going to do the same attack, but then it's going to recover keystream once it's found it. And you can see that they were really smart about picking 2048 as their number, because if you make it 4096, you're there forever trying to get keystream, because every time you try and get keystream, every time you do an extension, you've got to send everything you had before, and then to extend each one. So it slows down as you go, and it would like take ages. But your table would be only half as big, which isn't really like from 1.5 terabytes down to like 750 meg doesn't really save you a lot. But if you went the other way, your table goes up to being 3 terabytes. It takes 4 times as long to make. So yeah, I mean, I'll hand it to them. They picked exactly the right cut off. Yeah, definitely. But it's like, from a practical in the field perspective, how long do you really want to spend like faffing with someone's card? Yeah, because you've only got to build this once. So yeah, so I do think they've kind of got it right. If anything, I'd go up to 3 terabytes and get even less keystream. But but you can see the 2048 is just about doable. So yeah. Right, so we get all of that. We're going to bang that into a file. If I can type. Like that. Hello. Oh bollocks. That's balls that up, isn't it? Did it? That looks right. Right, so we've got, that should be key stream anyway. And then, right, let's just, no? Right, that might be because I need to plug that in. It's Friday morning, like, you know. Any moment. That is, yeah, I can feel it. Yay, okay. Right, so there's my table. So, search. Oh, crack 2 search. Crack 2. So it wants the keystream file. It wants the UID. Good point. And it wants the NR. So I just chuck in the. Oh. So I was really good yesterday. I managed to get this. Right. What's the key stream? Right. So it wants that's the UID for this tag, and it wants the nonce, the encrypted nonce, which is that one there. So it reports on every 100 bits because you just want to know that it's doing something, so that it's. And if it reported any more often, you just get streams of shit flying by, and it's all a bit pointless. And there's only 2048 bits, so it's only going to take a certain amount of time, but it is. So as I said before, all it's doing is going through 48 bits at a time, just slicing it through offset of 1 bit each time, and just looking them up in the table. So the table is made of 65,536 tables, so they're already sorted on the first 2 bytes of the key stream. Each of those files is around 24 meg in size. I mean, around because it's random as to which ones you end up getting, but they average out to 24 meg or 22 meg, around that anyway. And then they've been like Q sorted in C, so I'm just doing a B search on the, so you know, and find which table you want to find, map it in, and then just B search on it, and it just, yeah, either finds it or it doesn't. Or it finds it and it's wrong, you know, so obviously for every match it's also checking if the match is the right match. But it should complete any moment now. See, I've got just about enough patter to kind of get through this bit before it kind of completes. Well, I thought I had, maybe I don't. And there you have it. So it's found the RNG match, it's pulled out the state that it was. The bit offset was 1233, so it rolls back 1233 states, then rolls back through the initialization sort of setup bit. I can scroll that up a bit actually, yeah, so you can see. So I mean these swordfish like printouts are just there because like I actually checked it was by hand when I was coding it, and then never took them out when it was finished. So it's, you know, but it's doing the kind of maths. It's pulling out the B is the key stream that it pulls out from the PRNG, the 32 bits, and it's just XORing to pull out the nonce, and then it gets the key, and you've got an endianness thing because bits transmitted on RF are in big bit endian always, and that really messes with my head. So you've got to like rotate each byte and whatever, yeah. But hey, it works, and that there, wherever my mouse is, that there is the key for these tags. So it works. So, I'm impressed. I mean, right. So, let's move on to attack 3. So, attack 2, quite easy to code. Once you understood the little bits about jumping forwards, building the table is trivial if you don't mind waiting a week for it. If you want to do it in a day, you've got to put in some effort. But the code's out there now. The code's on GitHub, so you can just run it and it will build a table. But once you've got the table, it will work on every HiTag2 system. So you want to go and break into Volkswagen cars, then this is the same table that they would be using to break into cars. Now, cryptanalytic attack. This is quite fun. So the PRNG output is produced by this filter function f, which is made up of FAs, FBs, and FC. As I said before, each of the FA and Bs take 4 bits from the PRNG state and produce 1 bit of output. That feeds into function C, which takes 5 bits of input, produces 1 bit of output. They're all 50-50 biased, 1s and 0s. So this looks pretty good. Yeah. Well, here's the definition again, and this is the modified definition. So if you imagine that your LFSR shifts by a bit when you're, every time you produce a bit, you can either consider it before you've shifted it or after you've shifted it. Well, the reference design works differently to the format that the paper authors used. And so they work in the pre-shifted format, whereas the reference design works in the post-shifted format. Excuse me. So all of my maths works off these numbers, but they work on these numbers. So yeah, you just have it's just one out, but you just have to accept it. Right. What you can notice there is the first line, the first FA function. The bits it's taking are from a really wide section of the LFSR, from bit 34 upwards, which is 14 bits worth, whereas all the others are kind of 4 bits from a kind of a 6 or 8 bit kind of section. So they noticed that this was a bit of a problem, and the reason is because in a quarter of the cases, the most significant bit, the one produced by that FA function, doesn't actually affect the output you get from the PRNG. Right? So if you take the Boolean table for function C, which is 79072B287B, and you line it out as binary, which is what these 2 lines are here, all I've done is put the least significant bit version above the most significant bit version, and then I've bolded all the ones that match. So there's basically, from the first 34 bits of the LFSR, a quarter of the states you could end up in mean that only those 34 bits are going to determine the output of the PRNG, and the upper 14 bits that have no impact whatsoever, because all they're going to do is move you from the top row to the bottom row, or the bottom row to the top row, and it's already a 0 and it's going to become a 0, or it's already a 1, it's going to become a 1. So, and that happens in a quarter of the cases, which is enough of a bias that you can do something with it. So you end up with, it actually looks like this in a quarter of the cases. That left-hand block doesn't actually matter. Now, what this is reducing is, instead of having a 48-bit brute force problem, we've now got a 34-bit kind of brute force problem. And so what we could do, or what they did, is essentially brute force that 34 bits and find candidates that are valid, candidates that might be the key sort of possibilities, or candidates for the key, for the first 34 bits of the key, and then for all the candidates brute force the last 14 bits. So before we had this bias, we had to brute force the whole 48-bit space. Now we can brute force 34 bits of it and end up with a very small set of possibilities, and from those small set, brute force the last 14 bits. The difference is you go from 48 bits worth of work down to 35 bits worth of work, which is really significant in terms of how long stuff takes. So they invented function P. Function P tells you if you're in this state or not, and it uses the Boolean table. So this will tell you if you're in that one of those 1 in 4 states where the upper bit doesn't matter, the upper 14 bits don't matter. So I'm going to do my best to explain this. Right, so right early on, when the nonce XOR the key is shifted into the LFSR and it encrypts the nonce, we had this situation. And this is the kind of area we're working in, right? So NR, the nonce, is encrypted as the key XORed with the NR is pushed into the PRNG. That means the later bits of the nonce being encrypted are based on the earlier bits of the nonce that have already been shifted in. Like there's a relationship between the bits of the nonce and the encrypted nonce, the later bits of the encrypted nonce, which is bad, it turns out. Apparently that's a really bad thing to have done. And then it encrypts the challenge response next using the feedback function. So the first bit of the challenge response is encrypted when the thing is fully seeded, where you've got the key XOR with NR followed by the key is in the LFSR state. So if we were looking at the encryption of the first bit of the challenge response, we could, if that state there was one of these states where the upper 14 bits don't matter, and we were trying to guess that state, well then we'd only have to guess the lower 34 bits of that state, because the upper 14 bits wouldn't matter because it's already in this position where whatever they are, you're still going to get a 0 or 1 based on what the lower 34 bits say. Which means that only the lower 18 bits of the upper bits of the key XORed with the NR matter. So, NR, that would normally be 32 bits, we can get it down to 18, which means we're going to attack this bit of the process. So, if we were given the lower 16 bits of the key, which obviously we're not, we don't know what they are, but we're going to enumerate over those. But if we were given the lower 16 bits, we could find values that would sat for the upper 32 bits of that LFSR state, the key XOR with NR, that would satisfy P of X. Now we don't know the key bits, we don't know NR, but we could find random states that would satisfy P of X, so that the upper 14 bits didn't matter. And then that would mean that we could encrypt the first bit of the challenge response without having to know the upper 14 bits of the state. So instead of having to worry about an entire 48-bit state, we can worry about a 34-bit state for that particular point. So if we could guess a value for that, as we shifted in that value, we could extract the first 18 bits of the output, which is what is used to encrypt the nonce. Because we're shifting in 18 bits, and that will give us 18 bits, and we know the entire PRNG state throughout that process. Right? It started with the UID and the lower 16 bits of the key. We shift in 18 bits worth. We know everything that's going on, so we can work out the PRNG output, assuming we knew the lower 16 bits of the key, right? And then we can shift in 14 zeros to get it to the position where this 1 in 4 function P thing kicks in and encrypt the first bit of the challenge response. So we could get out the key bit at that point, the key stream bit at that point that would encrypt the challenge response. Given that you get encrypted nonces and encrypted challenge response values in pairs, we've got two sides of this equation, which we can now compare, we can work on. So this is the state we're going to get to, where we're going to encrypt the challenge response value. So for given lower 16 bits of the key, we're going to find candidates and we're going to test whether they encrypt the first bit of the challenge response correctly, which will reduce the number of options we have for the middle bits of the key. And then for all the ones that survive, we'll brute force the last bit. So we're going to we need 136 pairs, which is 34 times 4. So because it happens 1 in 4 times and there's 34 bits that it tells us about. So why that is, again, it's more magic. I'll say actually, Flavio Garcia, one of the authors, is at Birmingham University, and he's really good on email. He'll actually will answer your questions and stuff. So feel free to contact him. He's a nice guy. So we're going to divide the key into 3 sections: lower 16, middle 18, and upper 16. Is that right? Upper 14 rather. loop over the lower 16 bits, and for each possibility, each of the 65,000 possibilities, we'll do this entire rest of the process. So we're going to find values y, and y essentially will be the middle bits of the key XORed with the first 18 bits of the nonce. Right. So yeah, we were here. I don't really need to roll backwards. That's a very bright light. Is that new? Was that there before? Oh wow. All I can see is like flashing lights before my eyes. No, this is a good place to carry on from. Basically, we're going to capture 136 encrypted nonce and encrypted challenge response values, which is 34 times 4, because it happens a quarter of the time, and with 34 bits we're going to attack. So we'll loop over the first 16 bits. There's 65,000 times we're going to do this process, and for each time we're going to find all the values of y that satisfy this situation, given the lower 16 bits that we're working with. Because that will mean we can attack the first bit of the encrypted challenge response value. By testing our values of y against all the encrypted nonce and challenge response values, we'll find potentials for the middle bits of the key. And it'll be a small set, and then of the ones that are in that small set, we'll brute the last 14 bits. So we're going to do this, which is a modified version of what we had before. We're just going to do the first 18 bits of that process of encrypting the nonce. So we don't know the nonce and we don't know the key, but we know, but y is a value we're going to enumerate, right? So there's a lot of unknowns in this picture, right? But it won't matter because of the beauty of maths. So if we know that y is essentially the middle bit of the key XORed with the first 18 bits of the nonce, and we know the first 18 bits of the encrypted nonce is the first 18 bits of the nonce XORed with the first 18 bits of output from the PRNG, then we can rearrange those equations to do this, right? So we can say the nonce is the encrypted nonce XORed with the output, because it's just rearranging the XOR. We can then substitute that nonce into the equation we had for y, and then we can just move the output, PRNG output term, to the other side of the equals. Because it's all XOR, you can just rearrange stuff easily, can't you? So what we've got then is y that we're going to enumerate, or we're going to build a table based on. We've got the output, which would be generated from y, because we seed the random number generator and shift in y, and as we shift it in, we get the output. So we know, for any y, we know the first 18 bits of output that we'll get. So on the left-hand side of the equation, we know. And on the right-hand side of the equation, we've got the key, the middle bits of the key, which we're going to try and work out, and an encrypted nonce, which we've captured. So you can sort of see that we're reducing the unknowns so that we can work out the one unknown that we've got left. So this is the situation we're going to get to, where we've shifted in those 18 bits of y, and then we've captured the 18 bits of PRNG output. Then we shift in 14 zeros, and then get the next bit of PRNG output, because that'll be the bit that encrypts the first bit of the challenge response value. It's called AR. Now, AR, challenge response, is OXFFFFFFF, right? It's all ones. And the encrypted challenge response is that XORed with the output of the PRNG. Now, because of course that is all ones, that's the same as inverting the output of the PRNG. So we therefore know the first bit of the encrypted challenge response value is the inverse of the 32nd bit of output from the PRNG. So we're going to be dealing with the first 18 bits of output from the PRNG, skip 14 to get to this state, and get the 32nd bit, which will be the first bit, the inverse of which will be the first bit of the encrypted challenge response value. So we can now build a table based on, so we enumerate all of y, and for every y, get the 18 bits of output and XOR it with y, and map and then shift in the 14 zeros to get the inverse of the 32nd bit of output from the PRNG, and that's going to be our table values that we're going to build, and we're only going to deal with y's that satisfy function p, so that we can actually do this trick. So if we've got these equations that we've kind of come up with, the left hand side of those equals are what's in the table, and the right hand side is what we are going to map it against. You can see on the right hand side we've got the encrypted nonce, the encrypted challenge response value, which we've captured lots of, and the middle bits of the key. So we've now got a probabilistic attack to find middle bits of key that satisfy this arrangement. So what we do is we say that Z is going to be, we enumerate across all of the middle bits of the key that are possibilities, and set Z to the middle bit, our guess for the middle bit of the key, XORed with the first 18 bits of the encrypted nonce. And then we look to see if that's in the table. Now, it might not be in the table, right? And if it's not in the table, it doesn't tell us anything. But if it is in the table, we can look to see what the first bit of the encrypted challenge response value should be for that entry in the table. And if it isn't what the first bit of our encrypted challenge response value is for that pair, then we know those middle bits of the key are wrong, because it doesn't satisfy this relationship which it should satisfy. So we can then like ignore that one as a possibility. And so given 136 pairs, we will probably remove most of the middle bit options for the key that are wrong, and only leave a very small set. And for every one that passes, we then brute force the last 14 bits. It is literally magic. For me, this is like that bit in Swordfish where they've got the gun to his head and the girl, and he's like cracking TLS, whatever it was, right? This is that bit of the film. This is the code he's writing, you know. Because of course you write code to crack TLS, don't you? So yeah, so that's in a nutshell what I'm saying. So we enumerate across the first 16 bits of the key for every one of those possibilities. We build a table. We search for middle bits of the key in the table that are valid based on the challenge, encrypted nonce challenge response values. We brute force the last 14 bits for the ones that survive, and then the way we brute force is we test against two encrypted nonce encrypted challenge response values. We know it will satisfy one because that's how it's ended up in the table, which is why we do two to make sure. And all you're going to do is seed it with the key that you're trying and the encrypted challenge nonce, and then see if it decrypts the challenge response value. That's all we're going to do. So in terms of complexity, we have 2 to the 16 tables, because there's 16 bits in the lower part of the key. We're going to do 2 to the 18 encryptions to build the table for each of these, and 2 to the 18 lookups to find matches, and then for the ones that survive, 2 to the 14 brute force, which is only happens every now and again. It's negligible, doesn't really impact, which becomes 2 to the 35 operations in total, which is smaller than 2 to the 48, and therefore is why it wins. And it takes 16 minutes on average on my MacBook Air, but every time I look at the code, I realise I could have done stuff better. There's things that I'm recalculating every time it goes around the loop that I could have probably cached, stuff like that. So, so if you want to, become a rock star in the world of crypto, then for an out-of-date technology that no one's really using anymore, you could fix my code and make it better, and I'd be very interested. And it's on GitHub, so you can even submit like pull requests and fancy hipster things like that. So it was the hardest one to understand. I still don't know why the probability is a quarter and not a half, because whenever I look at the Boolean table, I see half. And I contacted Flavio Garcia and I said, why is it a quarter? And he went, oh, you're reading it wrong. You're reading the probability wrong. And then I was like, yeah, I still don't really get it. And he was like, well, it's because of this. He actually said, look at the Boolean tables, it's obvious. That was his reply. And I was like, dude, it's not. It's like, and so after 2 times of him not answering my question, like with something I could understand, I decided to stop asking because I don't want to appear to be a complete idiot. to him. And endianness really matters because the paper talk about bits in terms of the order they're sent in over the RF. So the first bit sent would be bit 0, and then the next bit would be bit 1, etc. But when you actually put them in a computer into variables, we have all our bits the other way around, and so you can easily be working back to front on what you think. And as it turns out, I was lucky and got it right first time, but I was at the point of kind of going, I will just guess that that's going to work and see if it works or not, and it happened to work. But if it hadn't done, I'd have had all this engine, this bit flipping nonsense to try. But it just messes with your mind when you're trying to remember what they're saying about the different bits and which ones they map to. So in terms of the commands, again, we're going to use sniff PWM to get the 136 encrypted channel response values, and then we're going to, which is just how we're going to capture them using that, 136 of them at least. You can have more. The code as it stands will take 1024 because I had to stick an arbitrary ceiling on it. The more you have, the quicker it will run and the more reliable it will be. If the values you get have any errors in them, the whole thing won't work. So you have to test the whole capturing bit to make sure you're capturing good values, which is hard to do if you don't know the key, because it's hard to test if they're valid or not. So you need to do everything you can in your power to get as good a read as you can, because one bit flipped in one of the pairs will trash the entire process, because something, the valid bit of the key won't get through the net. And then you just run HT2 crack 3 and it just works. So let's do the demo. Dun, dun, dun. Right, I'll tell you what we'll do. I will set up, I'll get rid of this disk. He says. Oh yeah, because of course you've got to spin the disk up in order to eject it, haven't you? Thank you. Right, so we'll get rid of that, and I'll plug in my other R fiddler just to sort of demonstrate this bit. So bear with me 1 second. I'm just setting this second R fiddler up as a reader. I need just need the key. Right, so we're in here, sniff PWMS. Right, so we're going to start sniffing. So if I overlap the coils, that's the start off, because the reader's constantly going start, because it's trying to like initialize. And if I get a card on there, you can see how quickly they're coming up. So you don't have to do this all in one session. You just have to use the same UID. So all of it just quickly demonstrate how quickly you can get like valid encrypted, non-encrypted channel response values. So if we just stop that, and if I list, in fairness, some of those were probably stored. Let's do that again. I'll just clear it, and because that's probably an unfair test. PWML, right? There are no. Oh, I can't type. There are no stored ones in there. All right. So I'll use that one. Just make sure I've got it. So it's just grabbing a load. These are really not random. If you read the code, you'll see how not random these are. But it's fine. It's only for testing purposes, this bit. Right. If I list them, yeah. Okay. Well, there you go. So we've got that many, like a page worth, in that amount of time. So the other thing I was going to say about this one was you don't have to. So these are obviously the right cards for this key for this system, but they don't have to be. As long as the system will take any HiTag2 card, like any UID, which cars won't. As I said yesterday, cars are programmed to the UID. They're whitelisted, but any building access control system kind of has to, because you've got 20,000 employees and then a load more join. Well, you can't predict ahead of time what their UIDs are going to be, and you probably aren't going to whitelist all 20,000 cards. So you can buy blanks and just use a random blank. As long as you use the same blank every time you're capturing these things, and then use that UID in the attack, you can attack it just by attacking the reader with a random card that you've got. So you don't actually have to have stolen or borrowed a valid tag for this attack. So if we cut to this window, I'll just bring it up so you can see. Are we in the right place? Yeah. So let's have a quick look. We'll do that doing the same card again. So I've got 136 encrypted, non-encrypted challenge response values. I'll show you what the file looks like. It's just like literally, blah. And then all we're going to do is run the crack. So it needs the UID, which is that value there, and it needs the file, which is that there. Now I've judiciously chosen a key that won't take 16 minutes. knowing how it searches, I picked a key in the right sort of space, so this will be relatively quick. But you can see these are all like the lower 16 bits of the key. That's how quickly it's getting through building the tables and searching the tables and not finding any valid middle bits of the key. So these are all ones. Well, there were all ones that we weren't having to brute force, and then it found a whole load that it had to brute force because they were candidates. But you can see that it's not brute forcing all of them, and that's the point: is that we've reduced the problem from a massive brute force to, and there's the key. So it's now cracked the key. On average, it takes 16 minutes. Total search space 32 minutes on this, MacBook. But if you had a faster computer with more cores, you could do it quicker. If you optimize the code, you could do it quicker. But that is indeed the key. So there you have that attack. So it's. I'll now quickly talk about limitations of future work, because you kind of should have some kind of end to this sort of thing. So the R Fiddler, this baby here, a very short read distance. If you're trying to read a HiTag2 tag, it's got to literally be touching the thing and not overlapping the wire, because that fucks it up, and you might need to move it about a bit. It's very, very sensitive and to being in the right place, and any amount of distance it won't read it. Now I have actually I experimented with different coils, having spoke to Adam Laurie about how to build your own coil, and all you do is wind wire around something round, obviously, but you buy this meter, an LCR meter, so you get an LCR 45. They'll measure inductance. So you know what inductance this coil is, 267 microhenries, I think it was, and you basically wind around until you get a coil that's around the same kind of number, and then use that. So around a strainer, which is about 9 inches, and that would get me another centimetre on the distance, and then I round it around something that's about that sort of size. I can't remember what it was. It wasn't a saucepan. It was something else. I basically raided the kitchen for anything I could find that was round, and wound stuff around it. So I had a coil that was about this big, and that turned out that got me 5 centimetres of read distance, which was kind of good. And then I wound it around the laundry basket, which was like this sort of size, right? And it wouldn't energise the card at all at any distance. And that's because you're only feeding it off USB. You've got a maximum amount of power you're giving it, and the field doesn't get sufficiently established in order to talk to the card. So there's a limitation there. I've asked Adam and Zach a number of times if there's any mods they could do to the board to like give it more power, or like any way you could attach a power supply, or anything you could do to the front end, and they just do not have an answer at this point in time. So so that's not an ideal thing. Now you all probably saw the Tastic from a couple of years ago, which was like a long range RFID reader for 125 kilohertz, but that's for like EM4102s or Q5s sort of tags. Now, so the standard one inside of there is a HID prox, which is like a car park reader. It's like this big, and it's got a really good read distance of like over half a meter. It's like really good, but it only reads up to 80 bits. Tags up to 80 bits long, and it expects a particular synchronization pattern. And if that synchronization pattern isn't there, it doesn't give you anything out the back in Wigand. So for a start, it's not big enough, because we would need to read more. If our tags happen to have the public mode kind of data thing turned on. I won't go into too much detail, but they don't talk HiTag2. They are really unsuitable for our purposes. The only long-range HiTag2 readers I can find are by Frequent, which sell to vendors, and Tagnology is a vendor that's bought that and put it in a box. They're really slow, as in the tag has to be in the field like for over a second before it can actually read the tag, which if you're just bumping past people in a red team kind of way, that doesn't really happen. You need to be like lingering in a lift with people and stuff like that. And the range they claim, which should be like up to 60 centimeters, and I'm like going, I'm not getting anywhere near. I was getting like 10 centimeters, and I was like, this is, and they were like going, oh, your cable's too long. So they flogged me a new cable for €50. They literally made a cable like that and charged me outrageous amounts of engineering time to make a cable, but that upped it to 18 centimeters, and I was like going, yeah, but this is still nowhere near 60, and they were like going, oh no, I think you found we said up to 30, and I was like, well, you didn't, but even so, it's still not 30, you know. I understand the up to bit, because that's like a joke in New Scientist every month, isn't it? But and they were then kind of saying, oh, it's to do with the flux density of your tags. Like you obviously haven't bought them from us. You know, you need to look it up on this graph, and it will tell you what the read distance is. And I'm thinking, I can't tell them that I'm reading other people's tags that I don't have access to the spec sheets for. That's not very fair. So. So I had a little moan about like their antenna being rubbish, and them not really knowing what they're doing, and they came back and had a moan about me not knowing what I was doing, and then we haven't spoken since. So, so I'm not a big fan of Tagnology. And in fairness, after I made it portable and built circuits and batteries and stuff like that to run it on, it's all stopped working. And I don't know if it because it overheated, or because my power supplies are too noisy for it, or what. It was working when I gave it to one of my colleagues. All I can say is that after I got it back from an engagement, it no longer works. So really sensitive to ripple in power supplies. So you can't run it off switch mode power supplies unless they're really, really high quality ones. So I was running off batteries, which was kind of working, but I toasted two really expensive batteries in the process. I've got no idea. So yeah, it's not easy. Tag emulation. So on the R Fiddler, you can emulate pretty much every tag that it can talk to, right? But there's no tag emulation for HiTag2, and I have been writing it, but you need hardware to test against, and I don't have any hardware. It is tricky to do, but it's doable. And so if anyone's getting hardware, I've got code that's 99% finished. We could probably add that. But if you had that, you could get someone's like UID off their actual tag by bumping into them in the pub, because you just start doing the first step of the handshake and get the UID, and then you can program your fiddler to be that UID, and then just go up with this and stick this on the thing, and it will just pretend to be the tag and capture the encrypted nonsense trans response values at the same time, which might be better than like having to actually have a tag for real. So potential future work. So inside the Fiacron, which is based on the Frost design, it runs off a PIC 16F. I reckon I could probably remove that and then drive the rest of the circuit myself, because I understand how the HDRC 110 works, which does the whole front end stuff. It's not trivial, but it's, you know, a few days of coding. It's not like impossible. And from that, I might be able to write something that's faster, so it's actually a bit more useful. And while I've got it all in pieces, I might try and turn up the power, so it might go a bit further. I might wind my own antenna, because their antenna is only 18 centimeters, and maybe the power can deal with a much bigger one. I haven't even tried, to be honest. I mean, it's so expensive. I didn't want to break it. It was like 1,300 euros for this kit, and it was like, you can imagine, like, you know, going back to your employer and kind of going, do you know that thing we bought? Can we have another one? Because I broke it. They're going to not be so happy. But the other idea is to build a high-power front end for the fiddler, and this is something I am going to try. So I'm going to get a HID prox, which is the car park reader used in the Tastic, which can't read what we're trying to read, but it does kick out a 125 kilohertz field on a really big range, and then so I'm going to use that to energize the tag, and I'm going to build a antenna for our fiddler that's bigger and use that in passive mode, and then I'm going to use a GPIO pin. So I don't know if you know the R fiddler, but it's basically, that's a PIC 32 in the middle of there, and if you buy the PIC 32 on its breakout board for prototyping, it's literally that half of the board. So that series of holes for pin strip and that series of holes for pin strip is the breakout board, and all Adam and Zach did was build their own analog front end and attached it to the side. Which is when you sort of think about it in those terms, it's like, it's actually, I kind of understand that a bit better now. So there's shitloads of GPIOs. So I'm thinking, use a GPIO, find the appropriate component, which might be a FET, or if I can find a suitably fast solid state relay maybe, or whatever, and then hook that into the field that's being generated by the Tastic, by the HID prox. I can then pulse that on and off to do PWM data to send the start off. The tag will respond with its UINT, which I pick up with our fiddler passively, and build my two-way thing by having a transmit and receive coil rather than having it all in one coil, and maybe get around it that way. So that's something I'm going to actually try at some point, probably next month. So other stuff would be the build the tag emulator, like I say, you know, and maybe build a portable one based on HDRC 110, but that would mean needing to understand analog electronics, which I don't really understand. It's like I don't even understand the data sheet that tells you how to do the equations. It's kind of like it's just beyond me. What's actually more likely to happen is that I'll stop playing with all this crap and I'll go and do crypto somewhere else. So I've got my site set on WPA2 at the moment because there's a academic break in that hasn't been weaponized. And I'm supposed to be writing a course called Fuck Crypto, which is crypto for pen testers. So it's not like the Stanford and Maryland courses at Coursera, which are really in-depth, clever courses about crypto, which are fun, but don't really tell you what you need to know as a pen tester. But they're a world away from the we're going to do a Caesar cipher, type attack, which is what you normally get. It's more like, how would you audit a TLS configuration? How would you spot that the crypto is bad, even if you can't break it? so you can tell a customer that they should be doing something different. You know, and I've yeah, I mean, the sort of things I've had on previous tests, right? On embedded, I do a lot of embedded stuff, and it's like there was a camera, and every bit of comms from the camera that went to the cloud was TLS, right? And after I convinced them to check their certificates and all that sort of clever goings, they were all secure. And there was one comms channel left, which was a local network one, so your mobile phone could watch the video from the thing on a local network. Obviously, you can't do TLS because you've got no PKI. So they were doing AES 128 encrypted with using CBC mode for the comms. So when the camera started up, it would, over TLS to the cloud, would pick a key and put it in the cloud. And when the mobile phone started up and went to the app, it would go to the same cloud over TLS and get that key. And then the two could communicate, right? Well, which is all really good, apart from the key they chose was based on the number of microseconds since the last second, right, using SRAND and RAND. So there was only 999,999 possible keys, right, out of the trillion that there should have been. So once you'd spotted that, which was like, you know, chuck the code into IDA and just kind of go, fuck me, that's clearly wrong, then you can build a thing that will handshake with the thing and crack the key in real time while it's doing the handshake, because you've only got like a million possibilities to go for. I've basically just built a table of all of the million keys and then just like tried each one, and it worked. So that's what, as pen testers, or as a pen tester, that's how I end up attacking crypto. It's not by staring at encrypted stuff and trying to work out what it might be or guess the algorithm or whatever, or doing some really clever kind of stuff. It's normally chuck it in IDA, have a look at the code, and then find ways of pointing out what's wrong with it. So that's what I'm supposed to be writing, is a course about that. And get a life, obviously, is the other thing I've been doing. So that's why I've not been around at the parties this week. I've been getting a life. Closing remarks. So attack 1 that I talked about yesterday in the start of this workshop is brilliant and uses keystream, recovers keystream to read the pages, but you can protect pages 1 and 2. And so attacks 2 and 3 will recover the key in the situations where attack 1 doesn't work. And attack 3 doesn't need a valid tag. You only need a tag that the system will talk to. Which is basically what I'm saying here. So yeah, attack 2 was the time memory trade-off with the big table and the 2048 bits of keystream. Attack 3 was one we just did with the 136 pairs and the tag. Now, if you really like this stuff, last year, so this paper's 5 years old, but last year Flavio Garcia, one of the authors, released another paper called Lock It and Still Lose It, and that's a different approach. So when you push the clipper to open the doors on your Volkswagen, or other car manufacturers are available, I should say, but they do own 23% of the European market, which is why they attack Volkswagen particularly. Then it uses, because the key, I haven't got one handy actually, but because the key has got HiTag2 RFID to de-immobilize the car when you put the key in the barrel, but the key clipper is over 433 megahertz, they use the crypto from the HiTag2 bit of the key to do the crypto over the 433 megahertz. So they can do the same attacks, but over the door opening as well as the turning on the car bit. But obviously trying to get 136 like challenge and nonce values is hard, because you'd be there for like weeks or months, like waiting for people to push the button in order to get those values. So they've got a new attack that only takes between 4 and 8 pairs, which is like a few days of hanging around them when they're opening and closing their car doors. And it works in 45 seconds. So when I was in Flavio's office, and he was like, do you want to see it? And I was like, yeah, well. And then he just ran it on his laptop, and like 45 seconds later, it's decrypted it. And it's very similar to the WEP attack. So it starts with a guess for a section of the key, and then it then extends it by 1 bit and works out the best possible So if you start with 16 bits, you've got 65,000 possibilities of what those 16 bits could be. So it finds the best candidates, the ones most likely to work probabilistically, and then extends that window by 1 bit and only uses the best ones from the previous step every time it extends it. And by the time you end up, that'll expand out bit by bit to 48 bits wide. Obviously taking less than a second per bit to do. So it's a clever thing. I've not implemented it yet, but I might do, just so I get practice at implementing yet another kind of useful thing. So the point of yesterday's talk and the point of this workshop, this is the last slide, is to say we can learn from academics. I know we shun them a lot, and we get really annoyed that we can't go to their conferences and they don't accept our papers because, oh, yet another O day, that's a buffer overflow. It doesn't really excite them. But some of them do have stuff we can learn from that I think is really interesting and useful and practical. So I think we should do more of looking at what they're doing, because I don't think many people in our industry are necessarily doing that. And that, as they say, is that. Any questions?